Let ABC be a triangle with circumcenter O and incenter I such that the lengths of the three segments AB, BC, and CA form an increasing arithmetic progression in this order. If AO equals 60 and AI equals 58, then the distance from A to BC can be expressed as m over n, where m and n are relatively prime positive integers. Find m plus n. First of all, the lengths of the three segments AB, BC, and CA, they form an increasing arithmetic progression in this order. So if we let the side lengths of ABC be A opposite angle A, little b opposite b, and little c opposite c, then C, A, and B form an increasing arithmetic progression in that order. So we can write A, rewrite it as B plus C over 2. Second of all, we see that both the circumcenter and incenter O and I of ABC are present in this problem. So we can use the incenter excenter lemma, which revolves around a point on the circumcircle of ABC that lies on line AI and is not equal to point A. That's point M, which is the midpoint of arc BC. So point M is here. The incenter excenter lemma states that MB equals MC equals MI. Let's call that common length T. We also know that AO is 60 and AI is 58. We see that we can use Ptolemy's theorem on quadrilateral ABMC. Let's do that now. We see that BT plus CT, which is the sum of the products of opposite sides, that's equal to B plus C times T, is equal to the product of the diagonals, which is T plus 58 times B plus C over 2. Now, if we multiply both the left and right side of the equal sign by 2, we get that 2t times b plus c equals b plus c times t plus 58. Cancel out the b plus c, we get 2t equals t plus 58. And subtract t from both sides finally to get that t is equal to 58. So we can replace t with 58. Now this has also allowed us to discover another fact, that I is the midpoint of AM, because both AI and MI are equal to 58. But also, AO is equal to OM, because they are both radii of the circumcircle of ABC. AO and OM are both equal to 60. So triangle AOM is an isosceles triangle, and it has base AM, with I the midpoint of that base. So it only follows from here that OI is perpendicular to AM. OI is perpendicular to AM. The distance from A to BC, from A to the foot of the altitude from A to BC. Let's call that X. The distance from A to BC is perpendicular to BC. That's point X here. And it certainly looks like the triangle formed by AX and the foot of the angled bisector here, let's call that D, is spirally similar to triangle AIO. And we're already halfway to proving that those two triangles are spirally similar. We just need another pair of equal angles. Recall that the circumcenter and orthocenter of a triangle are isogonal conjugates, which implies that they have the same angle with respect to the angle bisector of angle A. The orthocenter lies on line AX, somewhere here, point H. That's the orthocenter of ABC. It and the circumcenter are isogonal conjugates, which means they have the same angle HAI and angle IAO, since AI is the bisector of angle A. This angle and this angle here are equal. And therefore, since two of the angles are equal, the third must be equal as well. The angles at X and I are both right angles, and the angles at A are equal. Therefore, these angles are also equal. And therefore, we conclude that triangle AXD is spirally similar to triangle AIO. So the distance from A to BC that we need, which is AX, is equal to AD times AI over AO. And this is just equal to AD times 58 over 60. We know the lengths of AI and AO. And 58 over 60 is just 29 over 30. So all we need is AD times 29 over 30. But how do we find AD? Well, we can use power of a point at point D. If you notice, BD and CD are in the ratio C over B by angle bisector theorem, and their sum is B plus C over 2. Therefore, BD is equal to C over 2, and CD is equal to B over 2. The power of point D with respect to the circumcircle of ABC is the product of these values, which is BC over 4. And that's equal to AD times DM. We can find AD using Stewart's theorem on triangle ABC. Let's let AD equal little d and proceed from there. We see that D times C plus B over 2 times D plus C over 2 times B over 2 times C plus B over 2, which is just BC times B plus C over 2 cubed. That's equal to B times C over 2 times B squared C over 2 plus C squared B over 2. Remember, a man and his dad put a bomb in the sink. Man plus dad equals bomb plus sink. So D squared times B plus C over 2 plus BC times B plus C over 8 equals BC times B plus C over 2. Now, if you cancel out the B plus C everywhere, you get the D squared over 2 plus BC over 8 is BC over 2. D squared over 2 equals BC over 2 minus BC over 8, and that's 3BC over 8. So D squared is equal to 3BC over 4. Therefore, D is equal to root 3 over 2 times the square root of BC. Now, DM, well, remember that BC over 4 is equal to AD times DM. We know that DM is just BC over 4AD. That's just BC over 4D, which is BC over 2 root 3 times the square root of BC. And if you notice, BC over the square root of BC is just the square root of BC times 1 over 2 root 3, which is just root 3 over 6. So DM is equal to the square root of BC times root 3 over 6, and AD is equal to the square root of BC times root 3 over 2. So if you notice, DM is exactly 1/3 of AD. And their sum is AM, which is equal to 116. So if DM is 1/3 of AD, then it's 1/4 of the whole thing, so 29. And AD is equal to 87. So AD times 29 over 30 is just 87 times 29 over 30. And 87 over 30 can be cancel a 3 for 29 over 10. So 29 squared over 10, that's equal to 841 over 10, which can be expressed as m over n, where m and n are relatively prime positive integers. 841 and 10 are relatively prime positive integers. Find m plus n, which is 841 plus 10, and that's equal to 851. We are done with CIME I problem number 14. Thank you for watching this YouTube video. Please follow my channel if you would like to see more videos.